This session will deal with basic dosage calculations using alum, fluoride, chlorine, and a basic hardness calculation.
So before we start looking into a basic alum dosing calculations, I want to give a little bit of background on the products that are used, because in that you'll be able to see the percentages and know kind of what they mean and what they represent. So there are two main types of products you can get for alum. You could have liquid alum, which is a solution. You could have dry alum, which is a dry solid product that's hydrated, right? And in liquid alum, if we take a look at some of those properties, because we're concerned with how much product or how much aluminum ion we are adding, right? You may be reporting this on your monthly operation reports. You may be reporting how many pounds of product or your dosage in product milligrams per liter or your dosage in aluminum ion. And all this comes into play when you're trying to calculate how much of this alum you're applying to your water, whether it be liquid or whether it be dry. So in liquid alum, just a little bit as a background, because we'll be trying to use these percentages when going through some dosage calculations. If we take a look at the typical properties, right, it says that dry alum equivalent is 48.5%. So, and that's percentage by weight. So let's say, for example, you have 100 pounds. You're able to dump gallons onto a scale, into a little tank, right? Until you reach 100 pounds, right? So you have 100 pounds of this liquid alum, right? These product data sheets, or this product data sheet for liquid alum, this allows us to calculate how much equivalent dry alum we have in that solution, right? Without this percentage, we would not be able to calculate your product application or your aluminum ion dosages, right? So say you're able to weigh 100 pounds of the solution, right? And with the product data sheet, 48.5% is the dry alum equivalent, or the solid equivalent to that. Not solid, but the solid hydrated equivalent to that. That's represented by that formula, Al2SO4, SO4, and then 14H2O, right? That is what is meant by dry equivalent alum. So in 100 pounds, we would have 48.5 pounds of this dry alum, right? Which we would then be able to find, depending on how much I added, the dosage and the weight of aluminum ion or the weight of product, right? And be able to report or use in a dosage calculation. If we take a look at the dry alum, so again, the dry alum, that's just the solid itself and comes in bags and barrels, right? And with dry alum, you're making a solution, right? You're making a slurry of this chemical. You're adding so much to it, and even I think this one here is specifically, is recommended to target 10 to 15% by weight as dry alum. So it's telling you how much to make that solution. With that, the formula similar to the same as the one for the dry equivalent alum, Al2SO4 14H2O, right? So hydrated alum. We're able, using some basic chemistry, find what percent of aluminum ion is in that molecule, which we can then be able to use when we're calculating how many pounds of aluminum ion we're adding, right, to calculate a dosage. So this is what I mean by the percentages, right? Percentages of aluminum ion, percent of alum, dry alum, right? So if we take a look at dry alum itself, dry alum has a percent by weight of around 9%, meaning that if you have dry alum, right, up on a scale, you measure, I don't know, 100 pounds of it, right? 9% of it, or 9 pounds of those 100 pounds, will be pure aluminum ion, right? And you want to know this because in dosing, you may be reporting on your MORs either in pounds of product or pounds of aluminum ion, or you may be reporting your dosage in milligrams per liter of aluminum ion, right? And that's why that's important. And there's also some product data sheets that report the percent by weight of aluminum oxide, which can then, be further, you can use for further calculations to get the amount of pure aluminum ion. With liquid alum, right? With liquid alum, there is the percent by weight of alum as dry equivalent alum. Now, what does that mean? That means that if I have, say in this case, liquid alum is 49%, right? Percent by weight of dry equivalent alum. If I have 100 pounds of this liquid solution, right? 49 pounds of that, because it's 49% of that, 49 pounds of that is as if you had dry alum, right? Meaning that it's this molecular formula, right? Aluminum sulfate hydrated, right? And that allows you to then go through and calculate your dosage of aluminum ion, right? Knowing this percentage. And of course, if you take a look at the other two, percent by weight of aluminum oxide could also be found on some manufacturers' product data sheets, 8.3, and then around 4.4% by weight of pure aluminum ion, right? Which, having these percentages, you can find the dosage that you're trying to calculate.
Let's take a quick look at a basic alum dosing calculation. The problem statement reads, what is the alum dosage in parts per million of aluminum ion if a water treatment plant treats a source water with an average flow of 700 gallons per minute? A total weight of 150 pounds of dry alum is used during a 24-hour period. Dry alum contains 9.09% aluminum ion by weight. So with dosage calculation problems, you want to start initially with finding your million pounds of water, because we're going to be using our parts per million equation, and the pounds of water must be in million pounds of water for you to get the correct answer, right? And we're going to be overall finding the concentration, or the ppm, of aluminum ion, right? And in the problem statement, we're given how many pounds of dry alum we are adding in a 24-hour period, right? So we can then know how many pounds of pure aluminum ion we are adding, right? Let's take a quick look and go and walk through these steps together. So let's take a look, right? Step number one, we always want to start with converting your flow rate into million pounds of water, right? Because we will use the part per million equation to solve for the concentration, right? So step one, solve for million pounds of water. That's the same in any dosage calculation. You want to take this problem statement by chunks, right? First, convert to million pounds of water. We're given a flow rate, right? That is 700 gallons per minute flow rate, right? So we have to use conversion factors to see how much water was treated in a 24-hour period, right? So we know that there are 60 minutes in 1 hour. 60 minutes have to be on top so that units can cancel out. hour, right? Hours on the bottom, right? You always want to check, make sure that units are canceling out as you're going through the problem statement. We know that one day has 24 hours, right? Hours are canceling with hours on the bottom and top, right? And we know that 1 gallon of water has 8.34 pounds of water, right? This conversion factor and conversion factors such as these, a 1 gallon equal to 8.34, these will be given on the exam, right? And some more logical factors like these, I mean, everybody knows there's 60 minutes in 1 hour, one day has 24 hours, right? But any factors that require memorizing, right? These will be given on the exam formula sheet. So, after this, we take the multiplication of everything in the top divided by the multiplication of everything in the bottom, right? So that's 700 times 60 times 24 times 8.34, right? And then divide by the multiplication of everything in the bottom. The bottom, it's just 1 times 1 times 1 times 1, which is 1, right? We go through, we enter that in, we get 8,406,720 pounds of water, right, being used per day, right? But to be able to plug this into our part per million equation, we have to convert to million pounds of water. So this representation of it, right? And let me show you just a quick conversion you can use in which units will cancel out. This always seems to be pretty helpful for myself, right? Because there's multiple ways that you can get your answer to million pounds of water, and this is one of them, right? So if I have 1 million pounds, right, of water, isn't that the same as saying this representation of 1 m pounds of water, right? Isn't that the same thing? 1 million pounds written this way is the same as 1 m pounds written this way, right? Same thing, right? Pounds of water cancel out, and we end up in units of million pounds of water, which is what we want, right? We want it in this format of million pounds of water. So, and again, with dosage calculations, the water, the million pounds of water, you want to carry that out to the third decimal point. So if we write this down, 8.407 million pounds of water, right? Round it out to that third decimal point. So now we have found our million pounds of water, right? From our problem statement, next, let's handle and let's tackle the dosage, right? We know that we want to find a concentration in aluminum ion, right? And we're given that we added 150 pounds of dry alum in that 24-hour period. The problem statement also gives us how much percent by weight aluminum ion is contained in those 150 pounds. And that is 9.09% of that is pure aluminum ion by weight, which is what we want to find, right? So then it just becomes a percentage problem, right, for step number 2. Right? For step number 2, we know that 9.09% by weight of dry alum is pure aluminum ion, right? That's what we want, right? We know that we're adding a total of 150 pounds of dry alum, right? I'm going to show you a way, right? So now, in order to find my pure ion concentration, I multiply the dry alum by the percentage to get my pure aluminum ion pounds, right? So, a different way that you can look at this, and this way seems to be also pretty comprehensive if your percentages are not your strong point. If we take a look at these two equations, right? Pure is equal to your percent multiplied by your product, right? And if we take a look at this one, product is equal to your pure divided by your percent. So when you're going through a dosage calculation, right, and you get to the part where you have to use the percentages, you want to ask yourself, am I going or am I trying to find the pounds of the pure, or am I trying to find the pounds of the product, right? That will guide you to whether you have to times by that percent or you have to divide by that percent, right? In this case, we want to find, we are given the product as dry alum, right? We know that 9.09% of that weight is pure aluminum ion, and that's what we want to find. Our problem statement is asking us, what's your part per million in aluminum ion? So we're trying to find the pure, right? In which case the pure, right here, take that equation, pounds of aluminum ion, right? That's our pure, that's what we're trying to find, is equal to our percentage, which is 9.09, and again we want to have this in the decimal form. 0.0909, right? Multiply it by the product. In this case, it's the dry alum, right? So 150 pounds. That'll give us 13.64 pounds of aluminum ion, right? So this just means that there are 13.64 pounds in a 150 pound sample of that dry alum because we were given that percentage, right? Now, let's take a look at the next step, right? Step 3. We're gonna try to solve for that final step of the aluminum ion concentration, right? And that's where we use our part per million equation. And it can be written in two ways. It can be written in this format, where pound concentration in part per million is equal to your pounds of the chemical over million pounds of water, right? In this case, our part per million, we know we want it to be in concentration of aluminum ion, which is why we calculated, right, our pounds of aluminum ion. That's the pound of chemical, whether it be pounds of aluminum ion, pounds of dry alum, pounds of liquid alum, right? Depending on what they're asking in the problem statement, that's our pounds of chemical, right? It can also be written in the form pounds of chemical is equal to your part per million multiplied by your million pounds of water, right? Same equation, just solving for two different things. And this one is for part per million, and this one is for pounds of the chemical. If for any reason, right, in another problem statement or a problem, you're given the concentration you want to achieve, you can find how many pounds of chemical you need to achieve that concentration. So, in this case, it is asking us, what's our concentration part per million of aluminum ion? So we're going to be using this form of the equation. Our part per million is pounds of chemical. We recalculated that at the step above, right? 13.64 pounds of aluminum ion, right? Divided by, we calculated how many million pounds of water we had, right? Right above. 8.407 million pounds of water, right? We enter that in. We get a concentration of 1.62 parts per million. That's as aluminum ion. We have solved our dosage problem. So here is the problem statement that we just went through, a little neater, right? With any dosage calculation, you want to start by solving your 1,000,000 pounds of water, right? You want to take these calculations in a step-by-step basis. When you take it all at once, it's a little overwhelming, right? Step one, solve for your 1,000,000 pounds of water. The gallons that they give could be in, gallons, gallons, 1,000,000 gallons per day. It could be, in this case, as a flow rate, gallons per minute. They could give you your pounds of water, your 1,000,000 pounds of water in the problem statement already, right? It's your job to determine whether it's in the units that are required to be entered into the part per million equation, right? So in this case, we go through, right, the conversion factors. You want to make sure that you're checking those units, and make sure that they are canceling out. The next part, you have to read the problem statement and see what it's asking you, right? Is it asking me what is my concentration in terms of dry alum, right? My part per million in terms of dry alum. Are they asking me what my concentration is in terms of aluminum ion, right? That will then guide you into what calculation you have to do to get the pounds of the chemical that you need. In this case, right, they are asking us what is the concentration part per million of aluminum ion. We're given that we have 150 pounds of dry alum, right? That's the product. And we're given that 9.09% of that is pure aluminum ion. So we're given the percentage and we're given the product, right? You then go through with these two equations on top. You're trying to go from product to pure, right? So you're timesing that percentage, right? The next part, you use your part per million equation, right, in those two forms. What is it asking me? In this case, it's asking us for the concentration of aluminum ion, right? But if it was asking you how many pounds of the chemical do I need, right? The part per million equation can also be written in a different form to find the pounds of chemical to achieve a certain concentration, right? In this case, our part per million concentration of aluminum ion 1.62. Problem statement number 2, how many pounds per day of liquid alum are used if the flow rate is 12.7 million gallons per day and the dosage is 8.25 milligrams per liter of dry alum? The dry alum percent equivalent is 48% and has a weight of 10.46 pounds per gallon of that solution. If liquid alum shipments of 7,000 gallons are received, how long can a plant go without reordering? So it is a lot to take in. So let's go through and solve this problem using those exact same steps, right? Which is kind of how you want to take a problem statement such as this, is you want to take it step by step and be able to look at the logic and see what it is the problem statement is asking and where I am in the step and what I need to solve for. So let's start off with step 1. We want to find your 1,000,000 pounds of water used, right? So step 1, find our 1,000,000 pounds of water, right? So we need to have our water in 1,000,000 pounds of water for it to go into the part per million equation, right? So from the problem statement, we're given that 12.7 million gallons are used every day, right? 12.7 million gallons, right? In the other problem statement, we're given a flow rate, right? In this case, we're given the value in million gallons per day, and I'll show you a quick calculation that can be done so that you can have your answer in million pounds per day, right? So again, from our conversion sheet, we want to put gallons on the bottom, right? 1 gallon is equal to 8.34 pounds of water, right? We do a quick units check, right? Gallons cancel with gallons. Note that the million symbol still stays in the equation, right? We're just canceling gallons, right? And this will give us our units of million pounds of water, right? So we do the multiplication of the top divided by the multiplication of everything on the bottom, right? And 12.7 times 8.34 gives us 105.918. Remember, we're carrying that decimal point 3 places, right? Because it's in million pounds of water, right? And that our units, million pounds of water being used every day, right? So note how in this example, we simply carried on that million representation, right? To get us million pounds of water, right? If we had changed this and put 12 million as a number, right, we would have to divide by a million to get our units in million pounds of water, right? So, step 1, we have finished, got our answer in million pounds of water. And this problem statement, it's a two-part, right? First part asked how many pounds per day of liquid alum are used if the flow rate is 12.7 million gallons per day, and we're given a dosage, 8.25 milligrams per liter of dry alum. So in this problem, our product, right? Our product or our mixture is the liquid alum. Our pure is the dry alum, right? And that comes in handy when we use that percentage given in the problem statement, right? So first, let's take a quick look and solve for how many pounds per day of dry alum we need, right? Because we're going to use that in the problem calculations going on. So step 2, we want to solve pounds of dry alum, right? And in the problem statement, we're given a dosage, right? We're given a concentration, we're given a ppm of 8.25 milligrams per liter of dry alum, right? So from here, we use our part per million equation, and remember, it can be written in two different forms, right? Parts per million is equal to pounds of chemical over million pounds of water, right? It can also be written pounds of chemical is equal to your ppm multiplied by your million pounds of water, right? In this case, we have the concentration of dry alum that we're applying, right? So the form of the equation that we're going to use, because we need to find how many pounds of that dry alum we are using. So we're going to be using this equation here, right? We're being asked how many pounds per day, right? And we're given a dosage in dry alum, so let's go through, let's find that. So our pounds of chemical will be pounds of dry alum. Pounds of dry alum. We have our concentration, 8.25 milligrams per liter, times by 105.918 million pounds of water. Right? we go through and we times this out, and we get 873.82, and that's pounds of dry alum per day, right? So we have found first part of the problem statement. Actually, we have found how many pounds of dry alum, how many pounds of dry alum, right? And we are leading ourselves or setting up ourselves to find how many pounds of liquid alum, right, we are using, right, every day. So this part, right, step 3, we want to use that percentage given in the problem statement, right? And it says that dry alum percent equivalent is 48%, right? Which means that in a barrel of this solution, right? In a barrel of this solution, you get 48% of that is dry alum by weight, right? So the next steps, let's set up our equations to see if we need to find mixture or if we need to find pure, right? So pure is equal to your percentage multiplied by your mixture or by your product. And product is equal to your pure divided by your percent, right? And this step is very important, not only with alum calculations, but also with fluoride calculations, with chlorine calculations, right? You want to ask yourself, what is my pure and what is my product, right? In this case, our liquid alum, that is our product. That's what we're using. We're applying liquid alum. We are given the percentage in terms of dry alum. Dry alum is our pure, right? So we are trying to find how many pounds of our liquid alum we're using, right? So liquid alum, that is our product, right? And to find product, we take the pure, which we just found, right? Pounds of dry alum, we divide it by the percent, right? Let's go through and do that. So pounds of liquid alum is equal to pure, which is our dry alum, and we divide by the percent given. That is 48%, right? Well, 48%, can't use that, the whole number, so we use the decimal representation, right? We move 2 places to the left-hand side, and as a decimal point, 0.48 is our percentage, right? So 0.48, giving us a value, pounds of liquid alum of 1,820.46. That's pounds of liquid alum, right? So we have found the first part of the problem statement, which asked us how many pounds per day of liquid alum are used, right? And this is the amount of pounds per day, right? I just forgot to put per day here, right? So if we take a look at the next part, it's asking us if liquid alum shipments of 7,000 gallons are received, how long can a plant go without reordering, right? This is where our weight, because every gallon of liquid alum has a weight associated with it. In the problem statement, we're given that we have every gallon of that liquid alum weighs 10.46 pounds, right? So let's go through. Let's take a look at the next step. Step number 4, right? We want to find how many days. I want to find how long we can go without reordering. Right? We have how many pounds of liquid alum we're using. 1,820.46 pounds liquid alum every day, right? Per day, right? Well, we need to know how many gallons we're using per day, right? Because we know that we receive shipments of 7,000, right? And with that weight given in the problem statement, that's what we use to find how many gallons, right? So from the problem statement, we are given 10.46 pounds is the weight of liquid alum, right? Per every 1 gallon of liquid alum, right? Units cancel out. Pounds of liquid alum, pounds with liquid alum on top, and we get our units of gallons per day, right? So we take 1820.46 divided by 10.46 to give us a number. I'll put it down here. 174.04 gallons. And that's of liquid alum, right? Now we've found our gallons of liquid alum that we're using, right? The next step is to find the days that the 7,000 gallon batch will last us, right? So we start off with 7,000 gallons of liquid alum. I'll denote that by LA, liquid alum, just so that we have enough room in the paper, right? We know, right, from our previous calculation that we are using 174.04 gallons of liquid alum every day, right? So we'll use that as a conversion factor, 174.04. That's gallons of liquid alum in 1 day of operation. Units of gallons of liquid alum cancel out, and we get our units in days, right? That's how long we can go before the shipment runs out, right? So it's 7,000 divided by 174.04, and we get a 40.22 days, right? Which is roughly 40 days without reordering, right? So now we have found that last part of the problem statement, right? If we're receiving shipments of 7,000 gallons, how long can the plant go without reordering? Roughly 40 days, right? We have enough supply of that. So, just a little bit of a recap, right? Step number one, dosage calculations. You want to find your 1,000,000 pounds of water, right? Step number two, we want, in this case, we want to find how many pounds of dry alum we are consuming every day, right? We're given a dosage, 8.25 milligrams per liter of dry alum. We have our part per million, right? Our concentration. We have our 1,000,000 pounds of water. So now we can find how many pounds of chemical or how many pounds of dry alum we are using every day, right? We're setting it up so that we can use that percentage up on top of 48%, right? Once we have our pounds of dry alum, which in this case is our pure, right? If we're setting it up based off of those equations, right? Our mixture or our product is our liquid alum. So now that we have solved for how many pounds of dry alum we are using, right? Because we're given the concentration in the problem statement in terms of dry alum, we're able to find that weight. But from the problem statement, we need to find how many gallons we're consuming a day, right? So the next part is you want to ask yourself, what am I trying to find? Am I trying to find the product? Am I trying to find the pure? In this case, the product is our liquid alum, right? And our pure is our dry alum. Why? Because in the problem statement, we're given that dry alum percent equivalent in this solution is 48%. That means that if you have 100 gallons of this liquid alum, 48% will be the dry alum equivalent, right? So with that logic, right, we're not trying to find the pure. Our pure is our dry alum. We already have that, right? We're trying to find the liquid gallons of the product, right? Which is then why we use the second equation. Here, just to illustrate further, the mixture or the liquid alum is equal to the pure or the dry alum divided by that percent. Once we find that, we are able to find how many pounds of liquid alum we're consuming a day, and using that density in the problem statement, right, we're able to find how many gallons we're consuming in a day. And that's important because we receive shipments of 7,000 gallons of alum, right? We need to know how long that's going to last us. So if we know we're consuming 174 gallons a day, right, we can use that as a conversion factor to find how many days we have until we have to reorder, right? In this case, it's roughly 40 days or 40.22 days to be exact. In this section, we'll be looking at chlorine dosage calculations with the application of a chlorine gas, calcium hypochlorite, and sodium hypochlorite.
Before we dive in to a couple of chlorine calculations, let's take a look at the different forms of chlorine that are available for water treatment, right? You have chlorine gas, you have calcium hypochlorite, and you have sodium hypochlorite. Now, the chlorine gas, it's typically around 98 to 99% of available chlorine. We just say 100 for ease of calculations. Calcium hypochlorite, that is around 65 to 70% available chlorine by weight, right? And I want to discuss this because in the practice problems, we'll be using those percentages, and I just want to give a clear background of what that means. So when you talk about and say chlorine is 70% available by weight, that means that in calcium hypochlorite, if you weigh 100 pounds of this solid, 70% of that will be the pure chlorine, right? Pure chlorine ion. That's what it's meant by available, right? Available chlorine by weight. Sodium hypochlorite, it's a liquid, comes in concentrations, and it really varies, 3 to 19. The thing with sodium hypochlorite is that it degrades with respect to time, especially if you expose it to light. So you may get your shipment in at around, I don't know, say 14% available chlorine by weight. After time, if it's not consumed, right, that percent availability will start decreasing. Say 3 weeks later, you may analyze it and you may see that you only have 9% available by weight, right? And similar concept. When it's percent available by weight, say we have a solution that's 19%, you weigh so many pounds of this liquid, 100 pounds, right? At 19%, you have 19 pounds of pure chlorine in 100 pounds, right? Just wanted to give a little bit of that background before we start looking at some practice problems. Here's a very quick example of some of the product data sheets for sodium hypochlorite and also calcium hypochlorite. So if you take a look, sodium hypochlorite, and you can find the percent available by weight there on the product data sheet, and there at the bottom, available chlorine, and it's WT percent, that's weight percent, 11.9, and these you would get from your manufacturer once you buy the product. And with this percent available, right, we can then know, based off of how much liquid we added, we can know how much chlorine we're adding and be able to calculate a dosage. The next one here, we have calcium hypochlorite, and that's, again, it's a solid. And you can see there in the typical properties, your available chlorine, and then by weight, right, percent by weight, it gives you 65% available, right? Meaning that in 100 pounds of this powder, 65% is pure chlorine, right?
So let's take a quick look at one of the basic chlorine dosage calculations. First one's going to be dealing with gas, chlorine gas. So the problem statement, 15 pounds of chlorine gas were used in 24 hours. During this time, 1 million gallons of water were pumped. Calculate in milligrams per liter the dosage of chlorine applied. So we start off with our very first step that we start off when we're solving dosage calculations, and that is find your 1,000,000 pounds of water. Right? From the problem statement, we are processing 1 million gallons, right? So we can denote that by 1 gallons, right? That's per day. Right? We use our conversion factor. 1 gallon weighs 8.34 pounds, right? Gallons cancel out. We're left with 1,000,000 pounds per day, right? 8.340 million pounds of water per day, right? So we found our 1,000,000 pounds of water. Step 2. Step 2, in this case, pretty simple, pretty straightforward. It's asking us for a concentration, right? What dosage? I'm applying 15 pounds of chlorine gas pure, and I'm processing 1 million pounds of water, right? So we write down our part per million equation is equal to pounds of chemical over million pounds of water, right? From our problem statement, we're given that we're using 15 pounds of chlorine, right? We just calculated our million pounds of water. That is 8.340 million pounds of water, right? So we have our pounds of chemical, which is 15 pounds, and we have our million pounds of water. So we have the components that we need to find that concentration right? Our ppm. So our parts per million concentration, 15 pounds chlorine, right? Divided into 8.340 million pounds of water, right? To give us 1.80 parts per million, or milligrams per liter, same thing, of chlorine, right? And that's our answer. Just as a little recap, right? When you're dealing with dosage calculation problems, you want to first solve for million pounds of water, whether you're dealing with fluoride, whether you're dealing with chlorine, alum dosing. That very first step is solve for million pounds of water. You take the problem one step at a time. In this case, we found those million pounds of water. Step two, it's asking us for a concentration, right? The part per million equation can be written in two different formats, as we've seen some basic calculations with alum, right? Depending on what it's asking us, right? Here, the problem statement is asking us, what is the concentration? What's the ppm? We're already given the pounds of chemical. We've already calculated the million pounds of water, so we can find that part per million dosage. In this problem statement, a certain water supply applies 2 milligrams per liter of chlorine to the distribution system. Using the DPD test method, it was determined a free residual of 0.3 milligrams per liter exists throughout the distribution system. What is the chlorine demand? So, just overall concept of what's going on, right, in this scenario. Of the chlorine applied 2 milligrams per liter, you're only observing a 0.3 milligram per liter residual, right? So there's something in that water that's consuming that chlorine, right? If we take a look at the chlorine demand equation, chlorine demand is equal to your applied chlorine minus your residual, right? Chlorine. So, from the statement, we have our applied equal to 2 milligrams per liter, and we are observing a residual of 0.3 milligrams per liter, right? So our chlorine demand is the chlorine that is being consumed after we have applied an initial dosage, right? And that being chlorine demand is equal to 2 milligrams per liter minus that residual 0.3 milligrams per liter. Do the calculation. We get a chlorine demand of 1.70 milligrams per liter. So something in that distribution system is consuming that chlorine, right? Could be that there's some contaminant entering that distribution system that's consuming that chlorine, right? So that's the chlorine demand. This is the equation that you use. In this next problem, we'll be looking at the application of chlorine through the chemical calcium hypochlorite, which is a powder or solid. The problem statement reads, a water system processes 2.5 million gallons of water a day and applies 2 milligrams per liter of chlorine as a concentration. If calcium hypochlorite, given 65% by weight available chlorine, is used as the disinfectant, how many pounds of powder are used? So we want to start off these dosage calculations always with step number 1, which is find your million pounds of water. Find our million pounds of water. In the problem statement, we're given 2.5 million gallons, right, that are being processed every day. So we use our conversion factor. 1 gallon is equal to 8.34 pounds, right? And these conversion factors, or the conversion factors needed on the exam, will be given in a formulation sheet on the exam, so no need to memorize these. You just have to make sure that you orient them correctly so that units cancel out, or you will get the wrong answer, right? So the next step, let's take a look at units. Do a quick units check. Gallons cancel with gallons. We're left with million pounds of water, right? If we type that into our calculator, we get 20.850, and that's million pounds of water. So we found step number 1, right? Step number 2, right? Step number 2, it's asking us how many pounds of the powder do we need to achieve this dosage of 2 milligrams per liter. So the next step, we need to use the part per million equation to find our pounds of chemical pure chlorine needed to achieve that dosage. So part per million equation, pounds of chemical over million pounds of water. Can be written that way. Can also be written pounds of chemical equal to our part per million multiplied by our million pounds of water, right? In this case, in the problem statement, we're already given a dosage concentration is equal to 2 milligrams per liter, right? This is something that's already given in the problem statement. So now that's 2 milligrams per liter of chlorine, of pure chlorine ion, right? Of the pure chlorine ion. So the next step we have to do is we have to find how many pounds of chlorine ion do I need to achieve this concentration. So the form of the equation I want to be using, since I already have parts per million, I already have my million pounds of water, is going to be this one, right? Our pounds of chemical will be pounds of chlorine, right? Pounds of pure chlorine. Pure pounds of chlorine. And that's equal to our part per million concentration, 2 grams per liter, multiplied by our million pounds of water, 20.850. This gives us 41.70 pounds of pure chlorine. Right? So, since there's no way for us to be able to determine, exactly 41.7 pounds of chlorine in this powder that has, 65% available chlorine by weight, right? We have to use that percentage calculation to find how many pounds of the powder we need to use, right? So, step 3. We have our two equations. Pure is equal to your percent multiplied by your product, right? And you have product is equal to your pure divided by your percent, right? The next step, again, is we have to find how many pounds of the powder. We have the pounds of pure, right, which is the pure chlorine. We just calculated that. So what we want to find, and what the problem statement is asking, how many pounds of the powder do I have to add, right, to be able to add 41.7 pounds of pure chlorine? We have the pure, and we have the percent given in the problem statement. The percent is equal to 65% available chlorine by weight, right, which is 65, which is also equal in the decimal form 0.65, right? So that percentage, what that means is 65% available by weight. If you have 100 pounds of this dry powder, 65% of that, or 65 pounds of that, will be pure chlorine, right? Just trying to understand the overall basic concept of this, right? And that's where the percentage, right, calculation comes in. These are just percentage equations. And if your percentage concepts are a little hazy, you can write both of these equations down and just go through the logic, right? I have the pure chlorine, so I am looking for the product or the powder, right? I will use this equation, right? So our pounds of powder, which is the product, right? Pounds of powder, that's going to be equal to my pure, which is 41.70 pounds of chlorine, divided by my percentage, 0.65, right? If I type that into my calculator, I get 64.15 pounds of powder. And we have solved the problem, right? Our problem statement was asking us how many pounds of powder do I have to add to achieve a concentration of 2 milligrams per liter, right, of chlorine. Well, we did that by solving first for the pounds of pure chlorine I need to achieve that, right? And knowing that the calcium hypochlorite is 65% available chlorine by weight, right? I know that my pure is the chlorine ion, and I know that my product is the powder, right? And I'm trying to find the powder. Therefore, I use this equation here. Product is equal to pure over percent. So pounds of powder, 41.7 pounds of pure chlorine ion, divided by 0.65, which is the percent, to give us our total pounds of powder we have to add, right? And just as an overall concept, in this 64.15 pounds of this powder, right? Inside that, there is 41.7 pounds of pure chlorine, just to re-cement this concentration and a percentage kind of calculation, right? So just as a little recap, and in case you couldn't read some of my handwriting here, we have the problem statement here, which initially, again, step 1 is to solve for your 1,000,000 pounds of water, right? Step 2 is to see, okay, what are they asking me? Are they asking me for a concentration? What am I given, right? In step 2, in this case, we have to find the pounds of pure chlorine, right, we need to add, because we're using that percentage coming up to find the actual pounds of powder we have to add to achieve that concentration. Right? Step number 3, you look at what is it that I am trying to obtain, right? In this case, we're trying to obtain the pounds of powder, right? And you have to make that distinction between what is my pure and what is my product, right? We know our pure is chlorine, right? We have to find the pounds of the powder, right? So the product is what we're trying to find. You then select the proper equation, right? Product is equal to pure ion divided by percent, and you're able to find your pounds of powder. So let's take a look at an example problem that uses sodium hypochlorite, which is a liquid, right? And uses it as application for chlorine. So the problem statement reads, a water system processes 2 million gallons of water a day and applies a 2.5 milligram per liter of chlorine concentration, right? If sodium hypochlorite, 15% by weight available chlorine, is used as the disinfectant, how many gallons are used in a day? Assume 1 gallon of sodium hypochlorite weighs 10.4 pounds. Okay, so let's go through, let's take this step by step. When solving dosage calculations, again, step 1, will be to solve for your 1,000,000 pounds of water, right? So we go through, we set that up. 2 million gallons, right? are being used every day. We have our conversion factor, 1 gallon on the bottom, right? Because they need to cancel out. Has 8.34 pounds, right? We do a quick units check. Gallons cancel with gallons. We're left with 1,000,000 pounds, right? 16.680 million pounds of water. So we've solved for our 1,000,000 pounds of water, right? Now, step number 2. We have to look and see what the problem statement is asking us and what we're trying to find, because we're going to be using the part per million equation to find either the pounds of chemical, the part per million, depending on what's given, right? So let's write down both of our part per million equations. Let's see what we're given and what equation we need to use, right? Can be written like this, can also be written pounds of chemical is equal to the part per million multiplied by our 1,000,000 pounds of water, right? So in the problem statement, we're given the 20 million gallons of water, right? Which we converted that to 1,000,000 pounds. So we have our 1,000,000 pounds of water. Right? We're also given a concentration, a part per million of 2.5 milligrams per liter of pure chlorine, right? So our part per million is equal to 2.5 milligrams per liter chlorine, right? We're given the dosage, concentration, and we're also given the 1,000,000 pounds. So what we want to find from the problem statement overall is how many gallons of sodium hypochlorite we're using every day. From what we have, we can find the pounds of pure chlorine, right? Using this equation. Pounds of chlorine, pounds of chemical, part per million multiplied by 1,000,000 pounds of water to then be able to use the 15% available by weight to find how many gallons we're using in a day, right? So now that we know which one you're using, pounds of pure chlorine, right? Because that's what this will give us, because our concentration is in milligrams per liter of chlorine, right? Pure chlorine. So our pounds of chemical will be pure pounds of chlorine. 2.5 multiplied by 16.68 to give us 41.7 pounds of pure chlorine, right? So it does not end here, right? We need to find how many gallons of sodium hypochlorite I need to use, right, to achieve that concentration. So step number 3, right? In step number 3, that's where we use the percent available by weight. We know that in sodium hypochlorite, it is 15% by weight available chlorine, right? So this is the part where we use, right, some basic percentage calculation logic, right? And this is where I like to write my equations. Pure is equal to percent multiplied by the product. Product is equal to your pure divided by your percent, right? We already found how many pounds of pure chlorine we need to achieve that concentration. And now we need to find how many pounds of the product that is, right? In order to do that, we have to do a percentage calculation, right? We have the pure, right? So we have to find the product. So out of these two equations, we want to use this one, right? Because we have the pure and we have the percent. And we want to find the product, right? So let's go through and let's solve that. So if we take a look, the product, pounds, and that's of the solution, right? Pounds of solution, pounds of sodium hypochlorite, that liquid, right? Equal to the pure, which we found in the previous step, right? 41.7 pounds of chlorine. And we divide that by our percentage, 15, right? But 15, again, has to be in the decimal form. If we convert that, 0.15 is the decimal form. Right? So now pounds of solution equal to 278 pounds of solution per day, right? Type that into a calculator, that's what we get. So here we're still not done because what we've calculated is pounds of solution, right? The problem statement is asking us how many gallons of solution do I need? That's where we use the weight of 1 gallon of solution to find how many gallons of solution we're using a day, right? So we take it one step further, 278 pounds of solution, right, per day. We know that 1 gallon of solution weighs 10.4 pounds, right? So the 10.4 goes on the bottom because that's pounds of solution, right? And that cancels out with the pounds of solution on top to give us 1 gallon of solution, right, on the on the top part of that. That gives us 26.73 in units of gallons of solution. Gallons per day. And that's our final answer. Gallons of sodium hypochlorite used per day. So again, just as a little recap, right? In this problem statement, we're using sodium hypochlorite, which is a liquid, right? With any dosage calculation, step one will always be, let's solve for the 1,000,000 pounds of water. We want to take these step by step so that we don't get overwhelmed, right? So solve for 1,000,000 pounds of water, step one. You want to make sure that you're orienting those conversion factors accordingly, right? So that the top units cancel out with the bottom units, in this case gallons with gallons, right? To leave you with 1,000,000 pounds of water. Now step number two, right? Step number two, you will use the part per million equation, right? You want to write those two down in two different forms. Part per million is equal to pounds of chemical over 1,000,000 pounds of water, and pounds of chemical is equal to part per million multiplied by 1,000,000 pounds. Then you have to ask yourself, what am I given in the problem statement? What do I need to find, right? In this problem statement, we're given the part per million that we want to achieve, 2.5, right? So we have that, right? We're also given the million gallons that we're using. We have our 1,000,000 pounds, right? And then we have to then find how many pounds of pure chlorine, right, we need to achieve that concentration. Once you have found your pounds of pure chlorine ion, right, we then have to use that percentage that's given in the problem statement, right? Which was 15% available chlorine by weight, right? So just as an overall kind of concept, right? 15% available chlorine by weight, that means that if I weigh 100 pounds of this solution, right? Say I put it up on a scale, I weigh 100, I pour sodium hypochlorite, that liquid, into a big gallon drum, right? And I'm able to weigh 100 pounds of that solution. 15% of that, or 15 pounds out of those 100 pounds, are pure chlorine, right? So then it becomes a percentage calculation. And one thing you want to ask yourself, what am I trying to achieve, right? Am I trying to find the product, or am I trying to find the pure ion? In this case, we found the pure ion already, which was pounds of pure chlorine. So we have to find the product, right? And the product is equal to your pure ion, right? Pounds divided by the percentage, 0.15, to get your pounds of solution, right? That's your pounds of solution. That's your product, solution, liquid, per day. With sodium hypochlorite, since it's a liquid, we have to use the weight in 1 gallon of that solution to find how many gallons of that solution I'm using a day. And that's that final step here, right? In this next section, we will take a look at the application of fluoride in drinking water. There will be two practice problem examples, both using hydrofluorosilicic acid.
Now let's take a look at hydrofluorosilicic acid, or fluorosilicic acid, and let's take a look at some of the percentages, because it's very important that you understand the difference between the percent available of an atom in a molecule and the percent available of concentration in a solution, right? That's going to play a big role when you're doing and conducting fluoride calculations. So one of the most common forms of fluoride used is fluorosilicic acid. There are a couple more, and they are covered in detail in our fluoride section of this course. So with fluorosilicic acid, right? In that molecule, H2SiF6, right? If you do some calculations and find the percent available fluoride, right, in that molecule, you get 79.1% pure fluoride ion in the pure acid, meaning that it's just pure acid. But during manufacturing, the typical concentration that's available is around 23 to 25% pure acid, meaning, right, meaning that if you have, say, a barrel of this solution, right, and you're weighing out, oh, I forgot to say that it's 23 to 25% by weight available acid. So meaning that if you have 100 pounds of this acid, you put it up on a scale, you dump gallons of this until it reaches 100 pounds, 23 to 25% of that will be pure hydrofluorosilicic acid, right? And now, after that, we want to find how much of the fluoride ion we're adding, right, to calculate a dosage, because there are MCLs that you can't exceed, right? So what is done is it's a double percentage, and I'll show you here in the next coming slide to try to make you understand this concept. So yielding a percentage by weight of pure fluoride ion to be around 18.2 to 19.8. Just depends on the percent concentration of that acid in the solution that you're buying, right? Dive a little deeper into trying to understand this concept, because this will come into play once we start looking at some practice problems. So a hydrofluorosilicic acid solution, right? Again, it's made out of H2SiF6 is the chemical formula. And the solution, generally 22 to 25% pure acid by weight. So let's say we have a solution that's 25% hydrofluorosilicic acid, pure, right? We can see that if we have the acid solution, that's 25% of that, right? Which we could easily obtain if I have 100 pounds of this acid, right? 25%, or 25 pounds I have of pure hydrofluorosilicic acid. But that number won't tell me how much fluoride I'm actually adding to the water, right? I have to do an extra calculation and break down the molecular formula to find the percent available, the percent pure fluoride ion in that molecule to be able to calculate how much fluoride, or how many pounds of fluoride I'm adding, right? And this is covered in detail in the chemistry portion of this. So just as a high level overview, right? You have the atomic weights. You add up your atomic weights, right? From the atomic weights, you have how many of those are pure fluoride over the total atomic weight of the molecule to get your percent fluoride ion, right? To be 79.1% just pure fluoride in that molecule, right? So if we want to find how much fluoride we have in a solution, right, we would first times that weight, the weight of solution, by 25%, right, to get our pure hydrofluorosilicic acid. But then we would multiply again to find the pure, multiply again by the percent, right, to find the pure fluoride concentration, or fluorine weight in that solution. So if you do this, right, 25% multiplied by 79%, because 79% represents the fluoride concentration in the molecule, right? 25% represents the concentration of pure hydrofluorosilicic acid. Timesing those together, you're able to calculate that 19.8% of fluoride, 19.8% by weight fluoride in this solution. And again, that percentage, 19.8. It varies depending on whether you have 22% hydrofluorosilicic acid in the solution, 23, 24, 25, right? But just wanted to explain a little on that concept before we start going into some dosing calculations. A quick example of the product data sheet that you may obtain from your manufacturer. Of course, yours will be a little more in detail, giving you a specific number of pure hydrofluorosilicic acid, but you can see that here from the product specifications, you'll get the product, you'll get the percent by weight hydrofluorosilicic acid solution, right? And therefore, after that, you can then do some calculations to find what concentration of fluoride in milligrams per liter I'm applying to my water.
So the first practice problem reads, how many gallons of 25% hydrofluorosilicic acid, which is 19.8 pure fluoride by weight, solution will be required to apply 1 part per million of fluoride to 1 million gallons of water. It asks, assume that 1 gallon of acid weighs 10.4 pounds. So let's take a look and start off with our first step, is finding our million pounds of water. So step 1, find your million pounds of water. Right? The problem statement, 1 million gallons are processed. Right? Which can be denoted like this, 1 m gallons, 1 million gallons. We use our conversion factor. 1 gallon of water weighs 8.34 pounds, right? Do a quick units check. Gallons cancel with gallons. We're left with million pounds, right? So we have 8.340 million pounds of water. Step 2, right? We know that we want to apply 1 part per million of pure fluoride, right? So we want to use our part per million equation to find our pounds of chemical or pounds of pure fluoride that we're adding to achieve that part per million. So I start by writing down our chemical equation, our part per million equation. Pounds of chemical over million pounds of water, right? I also have pounds of chemical equal to your part per million multiplied by your million pounds of water, right? In the problem statement, we're already given our part per million. That's 1 ppm, right? We also just calculated our million pounds of water, right? That's equal to 8.340, right? So the equation that we're going to use, right, is this one, because we need to find our pounds of pure fluoride that we need to achieve that 1 ppm. So with that equation, pounds of pure fluoride, right, it's going to be equal to 1, which is the part per million that we want to achieve, times by 8.34 million pounds of water. That gives us 8.34 pounds of fluoride ion, right? So now we've found pounds of pure fluoride ion we need, right? Our next step, step 3,
is to find how many pounds of the solution we need in order to convert that to gallons and be able to know how many gallons we need to add to achieve that concentration of 1 part per million, right? So we want to solve pounds of solution, right? So let's take a look first and write down our percentage formulas real quick. Just as an overall concept and understanding. Pure is equal to your percentage times by the product, right? Your product is equal to your pure divided by your percent, right? So, step number 3, let's just walk through this step by step logic wise. We have our pounds of pure fluoride ion, and we want to go to our pounds of product, or pounds of solution in this case, right? So the equation that we use will be the second one here, right? So let's go through and walk through that. So pounds of solution, which is what we want, that's our product, pounds of solution. That's equal to our pure that we just calculated in the step before, 8.34, right, pounds of fluoride ion, right, pure fluoride ion, divided by the percentage. In the problem statement, however, it gave us two different percentages. It gave us 25% hydrofluorosilicic acid, and it gave us 19.8% fluoride ion, right? So what we have to do, and the decision that we have to make, is which one do I use, right? If I use 25%, that would be incorrect, because 25% represents the percentage by weight of pure hydrofluorosilicic acid, right? Of the whole molecule. That is incorrect, right? In this problem statement, it tells us that in the solution, 19.8 is pure fluoride. That is the percentage we want to use, the pure fluoride representation by weight in the hydrofluorosilicic acid solution, right? So 19.8 in a decimal form, 0.198, right? And that gives us 42.12 pounds of solution, right? We then want to go through and take it one step further, because they're asking us for how many gallons of solution do I need, right? We know the pounds. We know we need 42.12 pounds of this solution. Let's use that weight of the acid in 1 gallon given in the problem statement to convert to gallons of solution. So if I take 42.12 pounds of solution, right? We know that 10.4 pounds of solution, that's the weight in 1 gallon of that acid, of that solution, right? Pounds of solution cancel out. We're left with gallons of solution. 4.05 gallons of solution. And we have solved our problem, right? Let's do a quick little recap of the problem we just solved in the previous video. So again, you want to start off with solving for a million pounds of water when dealing with dosage calculations, right? Which we will use in the next coming steps. And step number 2, right? Depending on what you're asked, if you're given a concentration and asked for, pounds of solution or gallons of solution, right? Then you're going to have to find your pounds of the chemical. If you're given your pounds of chemical already and you're asked for a concentration, then you'll be able to use the part per million equation to solve for that concentration. So step number 2, right? You want to write down your 2 different forms of the part per million equation and ask yourself, what are they asking for? What do I need to solve for? In this case, right, we want to solve for the pounds of pure fluoride, right? Since we're given our 1 part per million of pure fluoride that we want to achieve, our pounds of pure fluoride will be obtained by using the part per million equation in the form of pounds of chemical equals parts per million multiplied by million pounds of water, right? And that gives us our pure fluoride concentration. The next step we want to achieve, right? We want to find how many pounds or how many overall gallons of solution we need to add to achieve that concentration of fluoride, right? So then you have to ask yourself, what do I have? What did I just calculate? In this case, I calculated the pounds of pure fluoride ion. And I know that I want to go to the product part of that, right? Your pounds of solution. That'll tell you what equation you use, right? And these are just basic percentage calculations, just simplified for ease of understanding, right? So product, your pounds of solution, that's pure ion, divided by your percentage, right? And again, percentage has to be in the decimal representation of that. And in terms of selecting the proper percentage, right? You may be given the percent of hydrofluorosilicic acid by weight in the solution, right? Or you may be given, in this case, the percent of pure fluoride concentration by percent in that solution. And that's what you want to use. You want to use the percentage of the pure fluoride in the solution, right? You find your pounds of solution, right? From there, you have to use that pounds of the weight of 1 gallon of solution to find your pounds, your gallons of solution. The next fluoride problem statement reads, how many gallons of 25% hydrofluorosilicic acid solution will be required to apply a 1 part per million of fluoride to 1 million gallons of water if the natural fluoride concentration is 0.3 milligrams per liter. Then gives 1 gallon of solution, weighs 10.2 pounds, right? Also gives pure hydrofluorosilicic acid, so in that molecule, H2SiF6, constitutes first 79.1% fluoride ion, right? So let's start off with step number 1. And that's always finding your million pounds of water. We know that we're processing 1 million gallons of water, right? We put the conversion factor accordingly, 1 gallon on the bottom, so that gallons cancel out, corresponds to 8.34 pounds, right? Gallons cancel out, we're left with units of million pounds, right? 8.340 million pounds of water, right?
So from the problem statement, however, it is telling us that there is already a natural fluoride concentration in the water, 0.3. So if there's already a natural fluoride concentration in the water, right, we have to subtract that from what we want to apply, right? Because what we add is going to be what we add plus the already natural fluoride water in concentration in the water, right? So just writing it out, fluoride applied is going to be equal to your fluoride required minus your natural fluoride, right? So your fluoride applied will be equal to the 1, your fluoride required, or what we want to apply, 1 part per million, right? And what the minus the natural fluoride concentration in the water, 0.3 ppm, right? That's equal to 0.7 ppm. That is what we want to apply. Since there's already a natural concentration of 0.3, right? 0.7 plus 0.3, that'll give us our total applied of 1 ppm, right? Does that make sense? So once we've determined that, we need to apply 0.7 and go into step 2, right? And we want to solve for the pounds of pure fluoride ion required to achieve that 0.7. Again, not the 0.1, because there is already natural fluoride in the water. 0.7 is what we use. So step 2, let's write down our part per million equations. Now the second form, pounds of chemical, is equal to the part per million multiplied by our million pounds of water, right? We already calculated the million pounds of water, right? We just found our applied fluoride of 0.7, right? So we have both ppm and million pounds. So the equation that we want to use is then the second one, pounds of chemical, right? In this case, it's pounds of fluoride, right? So pounds of pure fluoride ion is equal to that part per million, 0.7, right? Because that's how much we're going to apply, multiplied by our million pounds of water, 8.340, and that gives us 5.84 pounds of pure fluoride ion, right? Now let's go into step number 3. We've just calculated how many pounds of pure fluoride we need to add to achieve that, to add 0.7 ppm, right? So the next part is we use the percentage, right? A percentage calculation to find the pounds of product, right? The pounds of solution, so that we can then convert that to gallons of solution, right? So we start off by writing down our equations. Pure ion is equal to your percentage multiplied by your product. Product is equal to your pure ion divided by your percentage. So just using logic, right? We're going from pure ion and we want to find the product. To do that, we need the second part of the equation, right? Because we have the pure ion pounds and we have in the problem statement the percentage, right? So that's the one we're using, right? The product, in this case, it's pounds of solution. Pounds of solution equal to the pure ion concentration, 5.84 pounds of fluoride ion divided by the percentage. In this case, however, the percentage is a little different because it doesn't give us that, it doesn't give us a percentage of pure fluoride ion in the hydrofluorosilicic acid solution. It gives us the percentage of hydrofluorosilicic acid in the solution, and then it gives us the percentage of fluoride in hydrofluorosilicic acid molecule itself, right? So, for this part, a percentage is equal to the multiplication of both of those percentages. 0.25 multiplied by 0.791, which is 0.198, right? And for better understanding of this part, if you want to refer to the presentation of fluoride in this course, it discusses in detail why this is, right? So now that we have determined our percentage of fluoride, 0.198, right? We can find our pounds of solution. That is 29.5 pounds of solution. The next step, we want to find the gallons of solution. So 29.50 pounds of solution. We're given in the problem statement that 1 gallon weighs 10.2 pounds. 10.2 pounds of solution goes on the bottom, so they cancel out, right? 1 gallon goes on top. Pounds of solution cancel out. We're left with gallons of solution. So 2.89 gallons of solution is what we need, right? So let's do a quick little recap of the problem that we just worked out together. In the problem statement, we have taken into account the natural fluoride concentration, right? 0.3 milligrams per liter of natural fluoride in that water. So the fluoride applied, again, is the fluoride required that we wanna eventually have in the water, minus already your natural fluoride concentration to get your fluoride applied of 0.7 ppm. That's how much fluoride we're looking to add up to 1 ppm in the final water, right? We then go through, we solve for our million pounds of water in step 1. Step 2, we want to find the pounds of pure fluoride that we need to achieve and add for the 0.7 ppm, right? And then we're using 0.7, not 0.1, right? 0.1, you would be overfeeding your desired 1 ppm, right? 0.7 is what we want to use, since there's already 0.3 natural fluoride concentration in the water. So we write down both of our part per million equations. We're looking to find the pounds of chemical or pounds of pure fluoride, right? We go through and we times the 0.7 by 8.34 million pounds of water to give us our pounds of pure fluoride. The next part of the process, right? You want to ask yourself, okay,
Am I going from product to pure ion, or am I going from pure ion to product, right? What is the problem statement asking me? We have to find pounds of solution to find gallons of solution overall, right? So we are going from pure ion to the product. We then choose the correct equation, right? Which is product is equal to pure ion divided by percentage. We have the pure fluoride pounds, right? And for the percentage, again, for these fluoride calculations, right? If you don't read, right, that if you're not given a percentage of pure fluoride ion in the solution, right, in the overall solution, then you will have to multiply the percentage of hydrofluorosilicic acid by the percentage of pure fluoride in the molecule of hydrofluorosilicic acid. Again, please refer to the fluoride presentation in this course. It will cement this concept and illustrate why we have the times, right? You find your pounds of solution. We take it one step further to find the gallons of solution needed to achieve that 0.7 that we want to add, right? Giving us 2.89 gallons. This section on softening will deal with a very basic calculation on hardness. The problem statement reads, a source water has a calcium concentration of 65 milligrams per liter as calcium and a magnesium concentration of 35 milligrams per liter as magnesium. What is the total hardness as calcium carbonate? Assume calcium is 20 as equivalent weight, magnesium is 12.15 as equivalent weight, and calcium carbonate is 50 as equivalent weight. So, in order to calculate the total hardness, both the calcium and the magnesium concentrations must be in units of calcium carbonate. So let's go through and walk through how we would calculate that in order to add those up, right? Let's take a quick look at first the overall equation. Total hardness is equal to the calcium hardness added or plus your magnesium hardness, right? This basic equation was introduced during the water treatment part of this, right? Very basic. Total hardness equal to calcium hardness plus your magnesium hardness. Now, in order to be able to add these two up, right, since they're both given in calcium is given in terms of calcium in units, magnesium concentration is given in terms of magnesium, right? In order to add those up, we must first convert those to equivalent units of calcium carbonate. So for magnesium, right, be able to convert that to units of calcium carbonate. It requires your equivalent weight of calcium carbonate divided by your equivalent weight of magnesium at the bottom. Right? Times by your concentration of magnesium as magnesium ion. Right? And we are given these in the problem statement. So let's go through and let's find the concentration of magnesium as calcium carbonate. we're given that the equivalent weight of calcium carbonate is 50, that goes on top, divided by the equivalent weight of magnesium, which is 12.15, and we multiply all that by 35 milligrams per liter. And the 35 milligrams per liter is in terms of the magnesium ion, right? To give us a total of 144.03 milligrams per liter as calcium carbonate. That's the units we want them in order to add those up. So we found magnesium. Let's go through and do the calcium. And with calcium, milligrams per liter, that's calcium carbonate. That equation will be the equivalent weight of calcium carbonate on top divided by your equivalent weight of calcium at the bottom. And you multiply it by your calcium concentration as calcium ion. Right? We go through. Calcium in units of milligrams per liter is calcium carbonate, right? That's going to be equal to, from the problem statement, equivalent weight of calcium carbonate is 50. Equivalent weight of calcium was 20, multiplied by the concentration of calcium, which was 65 milligrams per liter as calcium ion, right? That gives us 162.50 milligrams per liter as calcium carbonate, right? That's our concentration of that calcium. So now we can go through and add those up. My total hardness, now in milligrams per liter as calcium carbonate, will be equal to 162.50 plus 144.03, right? Giving us a total hardness of 306.53 milligrams per liter as calcium carbonate. So, just as a little recap, right? For the total hardness, in order to add these concentrations up, since they are both in different unit terms, we have to first get them both in terms of calcium carbonate. Total hardness being the addition of the calcium hardness plus magnesium hardness, right? With magnesium hardness, you have the equivalent weight of calcium carbonate on top divided by the equivalent weight of magnesium on the bottom, multiplied by your magnesium concentration as magnesium. For calcium, you have equivalent weight of calcium carbonate on top divided by the equivalent weight of calcium on the bottom, multiplied by the calcium concentration in terms of calcium ion, right? We then go through and plug these in order to convert them to equivalent as calcium carbonate. Magnesium, we get 144.03 milligrams per liter. For calcium, we get 162.5, right, when we plug in those calculations. Then and only then can we go through and add these once they have those same units as calcium carbonate, with total hardness being equal to 162.5 plus 144.3, giving us a total hardness of 306.53 milligrams per liter as calcium carbonate.